Hello friends, I Pankaj Dumka welcomes you all to this discussion on fluid mechanics. Today I will be discussing with you about stream function. Now let us consider a two-dimensional incompressible fluid flow. Assume that this fluid flow is happening in a plane which is parallel to xy, and in this condition the mass conservation, that is the continuity equation, then can be written as del u by del x plus del v by del y, and that will be equal to 0. Now if you define a function psi which is a two-dimensional function x and y, which is depending on x and y and t, let us say, then this is defined in such a way that u is del psi by del y and v is minus del psi by del x, and if you replace the values of u and v in the continuity equation, then this becomes del by del x del psi by del y minus del by del y del psi by del x. Now this is the left hand side of the continuity equation. So if this psi is a continuous function of these two spatial coordinates and time, okay, then this becomes del 2 psi del x del y and del 2 psi del y del x. So if this is a continuous function, then they will be equal and cancelling out and resulting in 0. That is, they will be satisfying the continuity equation. Therefore, the stream function, this psi is called as a stream function. This is the stream function. What type of function is this? This is a two-dimensional stream function, and it is defined in such a way that it automatically satisfies the continuity equation. Okay, now the thing which you should all know is that this particular function was first given by or developed by or thought of by Lagrange. Now what is the beauty of the stream function? The beauty of this stream function is, instead of using two components for the velocity, we are simply using one variable, that is psi. And if at all in future these components are required, then we can derive back from psi these values u and v. Now let us dive into the mathematical aspect of this stream function first. So as I have already said that this is a function of two spatial coordinate, that is this is a two-dimensional function, then how can I write change in this psi? Del psi by del x dx plus del psi by del y dy plus del psi by del t dt. Now if the flow of fluid is steady, and if not, then or at any instant, at any time is equal to constant, means at any instant if we look this equation, then this term will vanish, because for a steady problem the variation of any property will not be there, and if it is at any instant, then change in time will not be permissible. So in both the cases, what will happen? This equation gets simply reduced to del psi by del x dx plus del psi by del y dy. Now how we have defined del psi by del x? Del psi by del x was v and del psi by del y was u. In one of my previous lectures, I have told you that the equation of a streamline is given by or given as dx by u is dy by v dz by w. So if you are restricting yourself to two dimension, then you can write this thing as v dx is equal to u dy, or minus v dx plus u dy will be 0. Therefore, on the right hand side you have the same expression. Therefore, as this is equation of a streamline and along that line minus v dx plus u dy is 0, that simply means if you place this stream function onto that particular line, so the change of stream function along the line will be 0, or the psi becomes a constant for that particular streamline. So a streamline is a line where the stream function is a constant, or a streamline is known by a stream function. We can say this. Therefore, we can represent any streamline in this two-dimensional plane as psi xy. So, if this is your two-dimensional plane and this is the flow, this is some streamline psi, so streamline, then this can be written as psi xy. So this psi is representative of this streamline. And if in a flow field you have number of streamlines, which is the problem, then each and every streamline will be having its own stream function. Got the point? So streamlines, on our streamline, the stream function is a constant. So stream functions can be thought of as the representative of streamlines. They are representing the streamline. So along a streamline, stream function is a constant. Now, come to the physical aspect of this stream function. What is the physical aspect of this stream function? So to understand this, consider a flow field. In a flow field, consider 2 points. Let us say A and B. Now this A point is thought of as a fixed point. Let us say this is a fixed point. Then you join these 2 points A and B. Then join another from another path. Let us say this. Let us say it is ALB and this is AMB. And assume that the flow field is steady. So if the flow field is steady, then if you assume that fluid is entering from here between A and B, fluid is entering with some flux, or discharge, let us say Q, then for the steady case, same amount of fluid will be leaving. So whatsoever is coming, that has to leave. So if you change the path from M to, let us say, some another path, let us say N, then also the same amount of discharge will happen. Okay. So A is fixed and this B is floating. So the rate across these lines, ALB, AMB, ANB, these all, rate across all these lines is a function of what? Is a function of this point B. That means if I extend this line further, from point B here in this direction, then what will happen? More amount of discharge can be accommodated, it can be allowed, and more can be leaving. Therefore, this point B position or the placement is what on which the rate of flow or discharge is depending or is a function of. And this positional function is what we called as a stream function. Okay, and this is, let us say, represented by psi, which you have already seen. Okay, if you consider the value of psi at point A as 0, if you consider this as 0 at this point, then you do a slight construction. Let me draw this AB again here. This is A and this is B. Okay, then you make another path. You make another path. Let us say this B prime, and assume that a streamline is passing through these two. So this BB prime is a streamline. Okay, then whatsoever is coming from AB will be leaving from AB prime. As BB prime is a streamline, so no fluid can cross streamline because all the velocity will always be along the tangent direction to the streamline. So if you extend this line further, let us say to B double prime, in such a way that this B double prime is at an angle 90 degree with the streamline B prime, and as I have already mentioned that the discharge or the flow rate across this AB is a function of what? Position of B, or this is what we represent as psi. So due to this there is an increment in psi. Let us say while moving from B to B prime there has been an increment in this psi, which is a representative of discharge. Okay, let us say this increment is del psi. Let us say this is del psi. So what is the discharge? If the velocity in this direction, that is in the direction of streamline, is let us say v, and this small incremental length, let us say del n, and let us say into the paper this is going by 1 unit. Okay, then this increment in discharge, because psi is now representative of discharge, so this increment of increment in discharge will be given by what? Will be given by this B double prime, that is del n times 1. This becomes the area through which the fluid is flowing with velocity v. Okay, so what you can do is you can write this v as del psi by del n. Okay, therefore the velocity at a point, at this particular point B, can be expressed in terms of stream function now. How? So if this del n is tending to 0, that means you arrive at this point B. So the velocity is limit del n tend to 0 del psi by del n, which is, let us say, del psi by this del n. So what have you got? You have got the velocity at this point B in terms of stream function psi. And how this is defined? It is defined that this velocity, the change in the stream function in normal direction to the velocity, will give you that particular velocity, because the change in stream function is in what direction? Is in this direction. And you are getting velocity in what direction? Perpendicular to this direction. That's why if you look here, what we have done is, when we are searching for velocities in x direction, we are differentiating this in a direction which is perpendicular to x, that is y. And when we are searching for y direction, we are moving in a direction which is perpendicular to y, that is x, that is del psi by del x. So y direction velocity, derivative with respect to x, x direction velocity, derivative with respect to y. Now this concept can be used to find out discharge between two streamlines. So how? Let us understand that. Let us consider in this two-dimensional flow field two streamlines. Let us say psi 1 and psi 2. Okay. Now, if this is fixed point sum A and this is B, then you can construct this small control volume and then forget about this psi 2 and psi 1 for the time being. Then what is the discharge which is moving across this line AB per unit width into the paper? That is given by what? That is given by x direction velocity is u and this is y direction. So let us say this is dy and this is dx. So it is u dy into 1. And in the y direction up downwards, it is minus v dx into 1. So if you can write this dq for this control volume, let us say this is C, then whatsoever is coming has to move out as the problem is steady. So this is u dy minus v dx, which is nothing but d psi, that is psi 2 minus psi 1. Therefore, the difference in the stream function between two adjacent streamlines will give you what? Will give you the volumetric flow rate with which the fluid is moving in between these two lines. Normal. So this is what it will give to you. So the difference in stream function between two adjacent streamlines gives the volumetric flow rate within the streamlines per unit width in the normal direction, and this is happening across a line AB. Okay, so if you are asking for the unit of this particular thing, then the unit will be meter cube per second is the unit of discharge per meter, or you can also write it as meter square per second. So friends, likewise, you can also go for cylindrical coordinates. The continuity equation in cylindrical coordinate for incompressible fluid is 1 by r del by del r rvr plus 1 by r del by del theta v theta. Okay. Now you have to define a stream function in such a way so that it satisfies these continuity equation. So if rvr is del psi by del theta and this v theta is minus del psi by del r, then these two will automatically satisfy the continuity equation. Therefore, in cylindrical coordinates, the stream function is how that is used to find out the velocity. That is, Vr is 1 by r and v theta is minus del psi by del r. So in this way, you can use this function to represent the velocities in cylindrical coordinate as well. Therefore, in this particular lecture, I have explained you what is a stream function and how it is used to represent the flow field. One more thing, whenever you have an irrotational flow field, then when you plug in the values of u and v in the rotation component for z direction, then you will be getting Laplacian of this stream function, and which is 0. So if the Laplacian of stream function is coming out to be 0, that simply means the flow field is irrotational. So friends, in this lecture till this point only, if you liked it, then please do like, share and subscribe. Thank you very much. Take care.